Welcome to the Explainer. Today, we are going to pull back the curtain on a core algorithm, one that's quietly running the show behind the scenes in social networks, web crawlers, even your GPS. Yep, we're talking about breadth-first search. Let's dive in. All right, let's kick things off with a question you've probably thought about. In your social network, how do you find the closest path to someone you're not directly friends with? You know, the friends of friends, but with the fewest handshakes in between. Where do you even start? Well, this is exactly the kind of puzzle that graph algorithms were born to solve. So to tackle a problem like this, we first need a map, right? We need a way to lay out all of these relationships, visually and logically. And the absolute perfect tool for that job is something called a graph. So what is a graph? It's actually super simple. It's just a bunch of dots, which we call nodes, and the lines that connect them, which we call edges. In our social network world, it's a no-brainer. Every person is a node, and a friendship is just an edge connecting them. Easy, right? Okay, but how do we represent this in our code? Well, there are a couple of popular ways. You've got something called an adjacency matrix, which is kind of like a giant spreadsheet mapping every single person to every other person. But that uses a ton of memory, especially since most people aren't friends with everyone. That's where the adjacency list comes in. It's way smarter for this kind of thing because it only keeps track of the connections that actually exist. Much more efficient. And check this out. This is what it actually looks like in Python. It's just a simple dictionary. It's so clean. Each person is a key, and the value is just a list of their friends. Super readable, super efficient. I love it. All right, so we've got our map. We know how all the connections are laid out. Now we need a plan of attack, a strategy to actually find that shortest path. And this is where the star of our show, breadth first search, makes its entrance. The best way to think about breadth first search, or BFS, is like dropping a pebble into a still pond. See, it doesn't just go in one direction. It creates ripples that expand outwards, right? That's exactly what BFS does. It checks all of your direct friends first. That's ripple number 1. Then it moves out and checks all of their friends. That's ripple number 2. It just keeps going, layer by layer, perfectly evenly. So to make this whole ripple effect actually work in our code, we just need 2 key tools. First, we need a queue. You can just think of this as a waiting line. First in, first out. Simple. And second, we need a visited set. This is basically our memory, so we can keep track of who we've already checked. This is super important because it stops us from going around in circles forever. Okay, let's actually walk through an example. We're going to start our search from you. The very first thing we do is put you into our queue. And right now, our visited set is totally empty. All right, step 2. We pull the first person out of the front of the queue, and that's you. We immediately mark you as visited. Then we look at all of your direct friends, in this case, Alice and Dob, and we add them to the back of the queue. Boom, layer 1 is done. So who's next in line? Alice. We pop her off the front of the queue, mark her as visited, and check her friends. Well, she's friends with you, but we've already been there. But hey, she's also friends with Charlie, and he's new. So we add Charlie to the back of the line.
Okay, Bob's turn. We take him from the front of the queue, mark him visited, and check his connections. His only friend is you, and we've already visited you, so there's nothing new to add to the queue. We just move on.
And finally, we get to Charlie. Let's say he's the person we were looking for all along, because we explored in those perfect expanding ripples. The moment we find our target, we know, we are guaranteed to have found one of the shortest paths. Here, it's just 2 steps. You to Alice, then Alice to Charlie. Done. So that's the logic. It's a really elegant and methodical process, right? But what does this actually look like when you sit down to write the code? Let's check it out. The code really just follows the exact recipe we just acted out. It's 5 simple steps. You set up your queue and your visited set, you add your starting point, then you start a loop that keeps going as long as there's anyone left in the queue. Inside that loop, you just pull someone out, check their neighbors, and if you haven't seen a neighbor before, you add them to the queue. That's it. And you know, in Python, there's a really efficient tool for this called a dequeue. That's D-E-Q-U-E. It's basically a special kind of list that's super fast at adding to one end and removing from the other, which is perfect for a queue. As you can see, the code itself is surprisingly short, and it perfectly mirrors the logic we just discussed. Okay, so this isn't just some clever, abstract puzzle. BFS is a true cornerstone of computer science, and for good reason. Let's talk about why this matters so much and where you see it in the real world. And this really gets to the heart of it, the absolute superpower of BFS. Because of that layer-by-layer ripple effect search, it doesn't just find any path. No, it is mathematically guaranteed to find the shortest path in terms of the number of steps. And that guarantee, that is everything. And look, it's all about choosing the right tool for the job. You've probably heard of BFS's cousin, Depth First Search, or DFS. DFS is completely different. It goes deep. It'll follow one single path all the way to the end before it even thinks about trying another one. BFS, on the other hand, goes wide. And for finding the closest connections, going wide is exactly what we want. So let's just pull this all together. Breadth First Search? It's not just a tricky question for coding interviews. It's the real-deal logic that helps Google's web crawlers map the entire internet. It helps your GPS find a route with the fewest turns because each turn is just a step. It's a fundamental building block for solving a huge number of real-world problems involving networks and finding the best route. And really, this way of thinking is so powerful. Learning to see a complex problem, whether it's a supply chain, the spread of information, or your own professional network, and model it as a simple graph of nodes and edges, that's a game changer. So the real question to leave you with is, what complex problem in your life is really just a graph waiting for you to explore it?